Something else we can look at when we look at Lewis structures is something called formal charge. Formal charge is kind of like oxidation numbers. It's a way to look at how are electrons distributed in my covalent molecule. Okay, and what we're doing is looking at, well, how many electrons does an atom end up with when it's bonded versus how many did it have before it was bonded. So kind of unsharing, we look at how the things share and then kind of breaking it apart a little bit to look at, well, where are the electrons really? Who has what electrons? And we use formal charges to kind of determine whether we have a reasonable Lewis structure. In a reasonable Lewis structure, formal charges are minimized. 0 is the best. Small numbers are better than large numbers. So if you have two structures and one of them has large formal charges and one has small formal charges, you would go with the one with small formal charges. Negative formal charges appear on the more negative, electronegative atoms. So if you come up with a structure where a negative charge is on the less electronegative atom, that one is less likely to occur. And then the third thing we look at is adjacent atoms should not carry a formal charge of the same sign. So opposites attract, likes repel. So we don't want two of the same charge next to each other, two positives or two negatives. So let's take a look at an example of what this all means. Okay, and I'll tell you how you calculate this. So we're looking at 2. This molecule would be CS2. Here are two structures for CS2 that follow all the rules for drawing Lewis structures. Everything has 8. You can see double bonds there, but everything follows the octet rule. So when I start looking at formal charge to figure out which one works out better, what I do is I look at each atom individually. And I say, well, first I look at how many valence electrons did that atom start with. Sulfurs start with 6, carbons start with 4. So then I figure out, well, how many electrons are assigned to that atom. So when I figure out how many electrons are assigned, what I do is look at the number of lone pairs. So there's 1, 2 lone pairs there. And I look at half of the number of bonded pairs. So there are 2 bonded pairs there. So there's 4 electrons there. So that sulfur gets 2 of the electrons, the carbon gets the other 2. So this sulfur has 1, 2, 3, 4 electrons that are part of the lone pairs, and then 2 of the 4 electrons in that bond. So that's how you get the number of 6 for electrons assigned. Same thing with carbon, same thing with sulfur again. So you'll notice that the formal charge in everything is 0 because sulfur has 6 valence electrons, and when we look at electrons assigned, it also has 6. When we come over to this other structure, you'll notice that carbon gets a -2, and then these 2 sulfurs, since one sulfur, the middle sulfur has a carbon bonded to it and a sulfur bonded to it, it's different than this other sulfur, which is only bonded to another sulfur atom. So that's where the 2 different formal charges for the 2 different sulfurs come from. This sulfur has a formal charge of 0. This sulfur has a formal charge of +2. So when we look at the formal charges, you can see that there are formal charges that are not 0 here. All the formal charges here are 0. So this is the better representation. Now you'll notice that this is symmetric. This better representation is symmetric. This other representation is asymmetric. So if you remember back to drawing Lewis structures, we said symmetric is usually preferred over asymmetric and compact is preferred over something that's spread out. And when you draw structures that are compact and symmetrical, you are minimizing formal charges. So let's take a look at this example. Now, when we go to calculate formal charges, there's an easy way to remember how to do that. So the formal charge on an atom is equal to the number of valence electrons for that atom minus, and this is very non-scientific, the number of dots plus the number of dashes. So let's take a look at these three structures, and we'll apply that formal charge equation. So on this structure number 1, the carbon has a formal charge. We're going to look at the formal charge of carbon. Here, we'll do this again. Formal charge of carbon equals 4 minus the number of dots, which is 0, plus the number of dashes, which is 4. So the formal charge on the carbon is 0. Now if I look at these two chlorines, they look identical. They have the same number of lone pairs, the same number of bonded pairs. So the formal charge is going to be the same on both of them. So the formal charge on each of the chlorines is equal to 7 minus the number of dots, which is 6, plus the number of dashes, which is 1. 6 dots, 1 dash. So the formal charge on chlorine is 0. And I'll come up here. The formal charge of oxygen is equal to 6, number of valence electrons, minus 4 dots, plus 2 dashes. So that formal charge is also 0. Formal charges of 0, this looks kind of symmetric. The two chlorines are the same, the oxygen's different. So that's not too bad. Now, when we come over here, you'll notice that the bonding pattern is different. The skeletal arrangement is the same, but the bonding pattern is different. So now if we calculate the formal charge of carbon here, again, it is going to be 4 minus 0 plus 4, no dots, 4 dashes. So carbon is still okay because it's still 0. Now you'll notice the chlorines are different. So now I have to calculate the formal charge on those two chlorines. So that's going to be chlorine 1. You have 7 valence electrons minus the number of dots, 6 plus 1 dash. So chlorine 1 is happy. It's got a formal charge of 0. The formal charge on chlorine number 2, however, is not 0. It has 7 valence electrons, but now there are 4 dots and 2 dashes. So chlorine picks up a positive 1 formal charge, which should already tell you, something's wrong, because chlorine is one of the more electronegative atoms. Not the most, that would be fluorine, but halogens like to be negative, not positive. Now when we look at the formal charge of oxygen, 6 minus dots plus dashes, so we have 6 dots and 1 dash. So oxygen has a plus 1 formal charge. So everything here is 0. And you notice the two chlorines have the same formal charge. Here the chlorines have different formal charges. So that's why this is less preferable. Even though it does follow all the rules. Everybody has 8. It has the right number of electrons. There are no issues with just following the octet. Now let's look at this last structure. Now you'll notice that the oxygen is in the middle now instead of the chlorine. So let's do this calculation. The formal charge of oxygen is 6 minus number of dots is 0, number of dashes is 4. So that has a formal charge of plus 2. The chlorines are identical, and their formal charge is 0 because they look just like the first one. So I'm just going to say that's 0. These chlorines look the same. The formal charge of the carbon is equal to 4 minus the number of dots, which is 4, plus the number of dashes, which is 2. And that gives carbon a negative 2 formal charge. So now not only do we have charges versus no charges, but chlorine is less electronegative than oxygen, yet it has the negative formal charge. So that would not be a preferable structure. Now, the last thing I want to talk about briefly is organic compounds, because organic compounds have lots of multiple bonds. Okay. So let's look at some of these things. We have things called alkenes and things called alkynes. Alkenes, the E-N-E ending means there's at least one double bond in that structure. Alkynes, Y-N-E, means there's at least one triple bond in the structure. So if you remember way back at the beginning of the year, the alkanes are all single bonded. So the ANE ending means single bond. So pentane is all single bonds. Pentene would have one double bond at least, and pentyne would have at least one triple bond. So you can see here the simplest alkene is ethene, the simplest alkyne is ethyne. And in parentheses you have the common names for these things, ethylene and acetylene. And then these are the systematic names. So here's what the structures look like. Double bond, triple bond. So you can represent these in a structural formula. This would be a Lewis structure. When we start looking at organic compounds, we call them structural formulas. Now, if there are oxygens or things with lone pairs of electrons, we would also show the lone pairs of electrons on the structural formula, which is basically the Lewis structure for a molecule. And then we also have things called condensed structural formulas, where we take the H's and pretty much condense them down. Since H's are always terminal, we know that these H's are just attached to the C. They aren't in the middle between this carbon and that carbon. So, and down here you can see how Lewis dots transfer into the structural formula. So we'll explore these topics in a little more detail in class also, and what they mean.